For question 61, we're looking at the combustion analysis of 0.44 grams of an unknown compound produces 0.88 grams of carbon dioxide and 0.36 grams of water. If the sample has a molar mass of 132, what's the molecular formula? So it's a combustion analysis, which basically means the unknown compound that we had that contained carbon, hydrogen, and oxygen, it was burned in the presence of oxygen and produced carbon dioxide and water. And so what we need to do, we need to take the mass of carbon dioxide, we need to take the mass of water and find the moles of carbon dioxide, the moles of water. And then once we know that, we can find the moles of carbon and hydrogen to find out how much was in the original sample and the mass of carbon and hydrogen in the original sample. And then we can find out how much oxygen was there. We can't do oxygen directly because there were two sources of oxygen. There's oxygen from the molecule and oxygen from the combustion reaction. So I have 0.88 grams of CO2, and I know that 1 mole of CO2 is 44 grams. You do the same calculation with water, 0.36 grams of water at 18 grams per 1 mole. I'm getting these numbers, right? That's the molecular weight of carbon dioxide. That's the molecular weight of water. That gives me 0.02 moles of CO2, and that gives me also 0.02 moles of water. What I need to know is how many moles of carbon and hydrogen I have. So in carbon dioxide, in 1 mole of CO2, there's 1 carbon, so I have 1 mole of carbon. In 1 mole of water, I have 2 moles of hydrogen because there are 2 hydrogens in every 1 molecule. So I have 0.02 moles of carbon, 0.04 moles of hydrogen. I need to convert these moles of carbon and hydrogen into a mass so I can find the remaining mass that responds to the mass of oxygen. So I know that carbon, for every 1 mole of carbon, I need 12 grams, and for every 1 mole of hydrogen, I would need 1 gram of hydrogen. So I have 0.04 grams of hydrogen, and I have 0.024 grams of carbon. My total mass is 0.44 grams. Of that, I have 0.24 grams of carbon and 0.04 grams of hydrogen. The remaining mass, 0.16 grams, needs to correspond to the oxygen. So I've got 0.16 grams of oxygen. I need to go through the same process. For every 1 mole of oxygen, I need 16 grams. So I have 0.01 moles of oxygen. Now I can find the mole ratio between carbon, hydrogen, and oxygen. To find the mole ratio, I have 0.02 moles of carbon, 0.04 moles of hydrogen, and 0.01 moles of oxygen. I want to divide each of these by the smallest number, and that's going to give me at least 1 whole number, so I'm going to divide everything by 0.01 because that's the smallest number, and that's going to guarantee I have at least 1 number set equal to 1. So I have 1 mole of oxygen, I have 4 moles of hydrogen, and I have 2 moles of carbon. This is my empirical formula. C2H4O1. We know that the molecular weight is 132 grams per mole. So we need to figure out how many times do I have to multiply this empirical formula to come up with the molecular formula. So in C2, I know carbon is 12, so there's 24. Hydrogen is 1, so there's 4. Oxygen is 16. So my empirical weight, by adding these three together, I get 44. So to find my molecular formula, I know that my molecular weight is 132 grams per mole. My empirical weight is 44 grams per mole. That goes in there 3 times, so I need to take the empirical formula and multiply that by 3 to find the molecular formula of C6H12O3. So the key to this problem was using the mass of carbon dioxide, the mass of water, to find moles of carbon, moles of hydrogen. Because both of them had oxygen, we couldn't use those to find the moles of oxygen. We had to find the mass of carbon, the mass of hydrogen, and then find the remaining mass that had to be associated with oxygen. Once we had that, then we could find moles of oxygen. Once we had the moles of carbon, hydrogen, and oxygen, then we could find the empirical formula, and then finally the molecular formula for this compound.